Morning, everyone. So yesterday we had a look at some of the math in related to errors. We talked about errors as being able to be represented with an absolute error, where it's in the same unit as measurement. Especially when I operate on numbers, when I do a plus or minus, the absolute errors end up adding together. That's true for both addition and subtraction. For multiplying and dividing, it was a little bit more complicated. What we did is we calculated the relative errors, basically how bad the plus or minus was on each of the measurements individually. I added those together, and then in terms of converting back to absolute, I need to multiply it back by the product. So what I'm hoping to do with you here, I'm going to practice through a few other questions, just carrying through error, just so that you get more familiarity with this. And then we're going to switch over and we're going to take a look at some just generic techniques when we do graphs. Why do we introduce graphs at all? What are the advantages, disadvantages? Just introduce some of the terminology. So let's first review our error, and then we'll go from there. So if we can just do this as a quick warm-up here. Let's start off with a circle. So first question. Let's start off with a circle, and I'm going to tell you that the radius of the circle is 2 plus or minus 0.3. So again, I wasn't the experimenter here. Someone has just reported that number. What I want to do in this question here is I want you to calculate for me, calculate the diameter, and calculate the area. Normally, I wouldn't ask a question like this here, but again, it's a nice way of thinking about it. So let's start off doing these two here. In terms of the diameter, we know the diameter is just double the radius. So we would expect to see 2 times r. In this case here, we're going to do this as a sort of simplification here. Well, if I go 2 times r, I would want to go 2 times 2.0 plus or minus 0.3. We are operating through a multiply. I'm going to show you the details of this, and then we'll come back and take a look at the shortcut. The question here is, how sure are you when you make this multiplication, how sure are you that this is actually a 2? Well, this one here is actually by definition. By definition, the diameter is always going to be double whatever the radius is. This number of a 2 is actually can be thought of. This 2 is a 2 plus or minus 0. That's a pure number. That's an exact number. It's basically, there's no uncertainty to it. It may look like a one-significant number, but it's actually 2.000 to infinity. I'm just going to show you the brute force of it, just to show you where a shortcut is going to come from. Imagine trying to do this. I'm operating a pure number from the definition with my radius. This one here, unfortunately, was a measurement, so this one here did have its error. Let's just punch this way through the multiply formula. When you multiply numbers, you need to go 2, sorry, I'm going to color code this for you here. You need to go 2 times 2. All right, so that part there is simple. When I do the plus or minus, because the operation here is multiply, I need to add the relative errors. The first one, like we said, was by definition, it was a pure number, an exact number. There's no error on that 2. However, there is an error of a 0.3 on the 2.0 that we had earlier. So there we go. That's adding the relative errors. This should still give you the percent, not quite a percent error, but the fraction error. Maybe that's a better way of saying it. This one here would still give you a fraction error, but I'm used to seeing errors written in the same units. I want you to convert it back to plus or minus. So how you do that here is you just re-multiply it by this 2 times 2 again. So let's try that here. Well, what's the diameter? If the radius was 2 and I'm operating on a pure number of 2, it's going to be 4.0. If you just did sig fig rules here, you might be accidentally saying, oh, 1 sig fig, 2 sig fig, this would be 1 sig fig. But like we said, this is a pure number. This is an exact number from the definition. There's infinite significant figures. So really, it's the second 2 that limits the sig figs. So we're actually 4.0. Let's calculate what our relative error is. If I just did 0.3 divided by 2, our relative error is, the decimal itself comes out as 0.15. So this part here comes out as 0.15. That means there's about a 15% problem on a 2 when you have a plus or minus 0.3. So this radius term here introduces a 15% relative error. The other one really has 0%. So in total, it is still, we actually have the same relative error. Same relative error of 15%. Except because the number has now been scaled up by 2, the number is now larger. If I take 15% on a bigger number, 15% should actually be a little bit larger. So if I go 0.15, I times it by 2 times 2, it's going to be 0.6. I notice if I just compare, it's also centimeters, if I just compare the size of the plus or minus, the size of the plus or minus used to be 0.3, but now it's 0.6. The absolute error has gotten bigger, not because the relative error has changed. The relative error here was 15%. Because the 0 over 2 introduced no other additional error, it's still going to be 15% error. It's just when I'm converting back to absolute, when I multiply off a bigger number, because the number has been scaled up, 15% on a bigger number ends up becoming a bigger error. If you can sort of look at the shortcut here, well, anytime you're operating a pure number, because there is no error associated, it's almost like what we did as a distribute. It's like 2 times the first 2, 4.0, 2 times the 0.3, just rescales it, and basically what it does is it keeps the same relative error, it just rescales it. Yesterday when we were talking about averages and we were dividing by a pure number, I think we had 3 numbers, and I said divide by 3, how sure are you that's 3? I know it's exactly by 3. Doing that same distribution work, if the numbers scale down by 3, the plus or minuses will also scale down by 3. You can also verify this answer here. Diameter can be thought of as actually radius plus radius. So you could also try it out here. 2.0 plus or minus 0.3. Let's add a 2.0 plus or minus 0.3. And we verify here 4.0 plus or minus 0.6 pretty easily, because through an operation of plus, the absolute error is just add. Now what's a little bit harder here is calculating the area. The area of a circle here, part B of the question, is pi r squared. Pi, although it is an irrational number, it's an unrepeating number, this one here is a constant. So this one here is also, this actually is by definition as well, as circumference divided by your diameter. But even though it's a non-repeating decimal, it is a number that's well known. There's no plus or minus to it. This is an infinite sig fig number. So what we want to do here is we want to actually take pi. In most cases in math, you would leave it in terms of pi. You'd leave the pi term out. But because I am doing sig figs and rounding here, I'm going to actually ask you to use the pi button on your calculator to actually figure out what the decimal actually is. So what I want you to do here is take pi, take the 2.0 that the radius is, plus or minus 0.3, and actually do the square. The problem at this point here is I don't know. Earlier when I multiplied by 2, I saw later on it just scaled in. Does it mean that the measurement squares and then the 0.3 gets squared? Let's just do it in detail here. When I square a number, it means multiply by itself. Now I actually see that it's actually, everything's just an operator multiply. I can actually do the multiply rule sort of all at once. So I want you to picture this here. To calculate the area, they want you to take pi, it's a constant. You're going to multiply it by one of the 2's, multiply it by the other 2. That is the answer. No matter how weird your error gets later on, that's going to be the area. That's the surface that's covered. On the other side here, again, pi is an exact number, 0 over pi. It's like pi plus or minus 0. There was no relative error associated with it. There is a relative error associated, 0.3 over 2, 15%, 0.3 over 2, 15%. And here we have our answer. Unfortunately, no, when I square something, it's not that the plus or minus gets squared. It's actually, we end up just adding the relative error. This one here earlier we had said was a 15% error, 15% error. Because I have both terms coming into play, I need to add those up. Overall, now you have a 30% error, a 30% taken off, rescaled over a bigger number. I haven't really typed in pi times 2 yet, so usually what I do is I just rewrite this here, and I can just punch it in all at once. I'm going to follow my sig fig rule separately, just for the math. So this is sig figs. I'm going to follow my error rules for the plus or minus part. So 2 times 2, use the symbol pi, so I'm getting 12.566. Calculator knows nothing about sig figs. It thinks exact 2 times exact pi. Based on my sig fig rules here, pi is a repeating decimal, it's a constant I know infinitely well. This is 2 sig figs, 2 sig figs. Based on my sig fig rules, I should be rounding to that 1's position. So it should be 13. Let's try the other case here. If I now have the relative errors as being added, this one here is going to now be 30%. What is 30% on pi times 2 times 2? What's 30% on this 12.566? Be a little bit sloppy with the error, 3.7699, because I know at the end of the day, I'm going to round my error to 1 sig fig anyways. When I round this to a plus or minus 4, make sure, so round error to 1 sig fig. And then do just one last check here. Where the error is actually positioned, make sure it lines up well. I would have made this a 13 anyways, perfect. The uncertainty is in the 1's position. The uncertainty and the error line up. And we'll do more of that in this lesson here. Make sure you have units here, centimeters squared at the end. If at this point here they don't line up, make them line up. So we saw that when you operate on pure numbers here, when I multiply by 2, it's like a distribute. When we did a square, it's not that the error plus or minus actually gets squared, it actually just doubles. So in that case there, I wouldn't memorize anything like that. I would just punch it through, see what the operations say. I'm going to do one more, just a typical math calculation with you, and then we'll continue onwards. Math calculation here, I didn't quite get to a mixed calculation yesterday, so let me just show you one of these. Again, fortunately in chemistry, we don't get too many of these mixed ones here. We saw the mixed earlier with sig figs. It was already hard because plus or minus had a different rule as multiply or divide. But we're just going to, just like our sig fig rules, you're going to just follow through. If it's a plus, follow the plus rule. If it's a multiply, follow the multiply rule. And just keep track of your sig figs, keep track of your errors as you go through. So here's a mixed operation here. One measurement is 12.3 plus or minus 0.4. Let's add that to 5.67 plus or minus 0.08, and I'm going to divide all this. There's your mixed calculation, 9.9 plus or minus 3%. All right. So first thing, as you're analyzing this number here, these guys here are definitely absolute errors because they are in the same unit as measurement, whatever unit I'm measuring. This plus or minus 3% is actually a relative error. So relative. You don't have to convert everything to absolute or everything to error. It depends on the operation that you're going to do. So doing my BEDMAS here, I'm going to do the plus first. Let's just try that top part, 12.3 plus or minus the absolute error 0.4. The operation is a plus. 5.67 plus or minus 0.08. Sorry, I'll space these out a little bit here. Remember, when we're doing add, we want to line up the decimal place. On the left-hand side here, should be able to do this math, 17.97. plus or minus 0.48. When I operate through a plus, the absolute error is add. So it was nice to already have the absolute errors. If this were the end of the question, I would round my error to 1 sig fig. It would have been a 0.5. I would make sure it's lined up with the sig fig rules. My sig fig rules here would have said 1 decimal place, 2 decimal place. It should have been only round to 1 decimal place here. Perfect. I would have done 18.0 plus or minus 0.5. But again, I know I'm not quite done. I need to crunch it to the next part of the calculation. So I've circled it, sort of how far along my guess is. It behaves like a 17.9, unsure at that tens place, unsure at that 0.4 place. And now what I want to do here is I'm going to take 17.97. Sometimes I write those numbers tinier just to remind myself I'm keeping those numbers around so I don't accumulate rounding errors, but it's not a large number, so it's not significant. Let's divide it by a 9.9 plus or minus 3%. What I want you to be really careful of here is when this is a 3%, it doesn't mean plus or minus 0.03. Not an absolute 3%. It's a 3% already relative out of 9.9. So if I really wanted to convert this back to absolute, I would still do something like, what is 0.03 out of 9.9? In this case here, because I'm operating through the math of a divide, it's perfect. I need to add relative errors. This one here already is the relative error. In fact, the top one, that's an absolute error, is not quite ready yet. I need to actually do that as a relative error. So let's punch through the quotient here. I'm going to take 17.97 divided by 9.9. So that's your answer. Plus or minus, how bad is the 0.48 on the 17.97? And then add, in this case here, remember, the absolute error was going to be 3% on 9.9. In this case here, I'm just writing the relative error. I can write this relative error directly as 0.03. Again, I want to scale it back into absolute, so times 17.97 divided by 9.9. Let's follow our sig fig rules first. So 17.97 divided by 9.9. When I operate on the numbers, this gives me here 1.815. Based on my sig fig rules, this behaves like a 3 sig fig number, even though I'm keeping that pesky 7 around. This behaves like a 2 sig fig number here. This one here should have been rounded to that 1.8. So keep the whole number in your calculator. It should have been rounded to here. I might still need to do some rounding depending on what happens to the error. For the error part, you can be a little sloppy because in the end, we're going to round to 1 sig fig anyways. I do the 0.48 divided by 17.97, add a straight 0.03. I multiply it off my quotient again. And I'm getting an error plus or minus of 0.1029, give or take. I'm going to round my error to 1 sig fig. So let's round this one to plus or minus 0.1. And whew, luckily for us here, this ended up at 1.8 plus or minus 0.1. Again, here's just a check for yourself. Round errors to 1 sig fig. That's why you can be a little sloppy. You don't need to follow sig fig rules through this part here. And then make sure your uncertainty, notice your measurement actually has 2 sig figs, that's fine. It's just that the guess is actually in the same tense position as the error is. Again, I should have done a question where you actually didn't have lined up nicely, but let's just do it as a what if. What if when we actually did these calculations, what if I ended up with my sig fig rules actually let me keep 1.82 and I had an error of 0.1. In that case there, it doesn't line up. The error is in the tens place, although my guess is in the hundreds place. In that situation, the error actually limits the precision on your measurement. I would then write out the answer as 1.8 plus or minus 0.1. Even though my sig fig rules may have actually allowed me to keep that second decimal place, because the error was so low precision, I need to round it off. Again, vice versa here, it is possible that I have the number, maybe what if it comes out as 1.8, but then when I crunch through my errors, maybe it's just 0.02. In that case there, maybe my sig fig rules say, nope, you can't go any beyond this first decimal place. You can't just suddenly go 1.80, right? That would be overly precise for the equipment we have. What we have, however, here is an error that's way too tiny. Our error is 1 sig fig, that's a good idea, but this is in the second decimal place. I want to round this to the first decimal place so it matches up with my guess. In that case, usually it's a 5 that rounds upwards. If I round this one here, it would be 0. Well, it doesn't make sense. Just for rounding, it ends up being 0. So in this case here, strange as it may seem, I'm going to still write this number, 1.8 plus or minus 0.1. So if I would have fit in just a size of 0.02, it would definitely fit in a size of 0.1. So that's how you deal with errors here. Do that check at the really end here. Make sure your final errors have 1 sig fig, and make sure your uncertainty lines up with it. Okay, so do practice your way through the worksheet here and practicing through propagating errors through plus or minus, multiply and divide. There is the odd mixed calculation for you to try out as well. We're going to do a quick section on reading scales. How do we actually figure out how big of a plus or minus I should do? And then after we do that, we're going to switch over, take a look at the summary on graphing from earlier. So this part here is just a quick section on how do we read scales. How do we read, based on the equipment itself, how do we associate how big a plus or minus is? At the end of the day, there's no hard and fast rule that it has to be a certain size. It's up to you as the experimenter. It's up to you in interpreting how good your devices are, how big a plus or minus is going to be. We're going to separate our scales into 2 types. First type here, we're going to do our what are called analog scales. So there's no digital, there's no electrical numbers, electrical displays, things like that. For analog scales, usually what we do, we're going to, here's a process we're going to work through in our first lab. You're going to find, right better here. We're going to find first the numbered divisions. Find out the actual printed numbers on your rulers, on your graduated cylinders. Find the numbered divisions. Then you're going to find the unnumbered divisions. And then depending on the actual device, usually we can guess one more digit. So let me just show you this process here. So let's say I'm looking at a ruler. So here's my ruler. I have the 1, 2, 3 like that. Okay. So sometimes it's hard to identify what's numbered and what's unnumbered, but this is just a nice hint for you to try to get at how precise something is. Let's say I have a pen cap or something. It matches up to that length there. The question here is, should I, we sort of did this here, should I say the length is 1 centimeter? Should I say it's, 1.2 centimeters, 1.29 centimeters, 1.296 centimeters? You see there's an inherent ambiguity with, well, I know the ruler is there, but how many digits should I be keeping, let alone what should the plus or minus be? So in this case here, this is sort of best case scenario. My numbered divisions are where I have the printed numbers. So how far are the printed numbers apart from each other? Well, the printed numbers are 1 centimeter away from each other, right? That's where the 1 and the 2, they're off by 1 centimeter. This is a good ruler here, so I have the millimeter tick marks here. It's divided into 10 even spacings. You can go 1 centimeter divided by 10, although you could say 1 millimeter. I just want to keep it in the same unit, so I'm going to call it 0.1 centimeters. Because this one here gives you so many tick marks, because it's in so many little spacings here, what you're going to end up doing is you're going to guess one more digit. The unnumbered division The tick marks already assure you not just you're sure about the numbered part, you're even sure about, yeah, it's past the second tick mark, but not quite past the third tick mark. You are allowed to guess one more position. I would guess this one here. I would not guess the 1.296 because if that 9 that I eyeball is actually off, if it was actually 8 something, then there's no reason to keeping anything afterwards. So that explains to you how we round our decimals for the measurement. But now what about the plus or minus? Normally what we do, our error, error is usually half the unnumbered division. So the tick marks that we have. So the unnumbered division for me was 0.1 centimeters. If I just take half of 0.1, I'm going to associate error of plus or minus 0.05. Now, why do I do that? Let's just zoom in here. So I have a 1. So I have a 2 there. My object here is coming upwards to maybe about there, right? So just line it up for yourself. If I let myself be wrong 0.05 up, 0.05 down, you'll notice I've created the gap. So 0.05 up, 0.05 down. I've created a gap that's 0.1. That 0.1 is exactly matched up to the unnumbered division. I might be still eyeballing my value 1.29. I still might totally be off at that 9 position. So it could be 1.28, I wouldn't be surprised, 1.27, whatever. But I'm letting myself be wrong. 0.05 up, 0.05 down. I've just created a gap size naturally as the tick marks would have been. This should be sort of, it's a nice rule of thumb, right? If I can see it's between these two tick marks here, if I now create, I'm in the middle of the tick mark, and I now create a size half wrong up, half wrong down, I should be able to, at least in that precision, be able to tell what my reading is. So in this case here, 1.29 plus or minus 0.05, you're just going to do a check for yourself, sort of like what we did with averages when I didn't have the plus or minuses. Check that the error is 1 sig fig, and check that the measurement, not that the measurement needs 1 sig fig, but check that the guess is in the hundredths position, and that lines up with this guess here. So that's where this whole notion, let's do half in the unnumbered division, make sure you have units at the really end of your measurement. Now, if you're more confident than that, you can say 0.04 or 0.03. But this is just a rule of thumb here. At the very least, you should be able to do 0.05. Now, this ruler here was sort of best case scenario because it divides sort of one increment into 10 spaces. Obviously, you can guess the next digit. What if we had a sort of beaker, right? Beakers, they're notorious for not being really good in terms of their detail. Let's say I have a beaker, I have a 50, I have 100. Depending on the manufacturer here, sometimes you will have more numbers, sometimes you have more tick marks. So you really need to look at that exact beaker. This one here might be a 100 ml beaker. In fact, for a 100 ml beaker, you might find that it actually doesn't quite get up to 100. It's sort of said, even after the top mark here, yeah, in total you can hold about 100, but really beakers aren't assumed to be very precise anyways. So the question here is, what plus or minus or how many decimal places should I be able to read a reading to? So let's say my liquid here, we read bottom of the meniscus. We sort of account for water's adhesion here, and we try to figure out, well, how precise that number is. So let's go through this procedure here. How about your numbered divisions? How about where you actually have numbers? How far apart are these numbers? So in this case here, I had a 50. Maybe I'll put the 100 back in there. My numbered divisions here are off by 50 milliliters, right? I know at least within 50 milliliters, give or take, even though I know beakers are not very precise. How about the unnumbered divisions? Again, this is just a hint for yourself. Sometimes it's really hard to find numbers. Sometimes you have too many unnumbered divisions. But it's just a nice technique for you to start getting a sense of how many decimal places should I keep my measurement, as well as my plus or minus. My unnumbered divisions, this time you'll notice, instead of taking your numbered gap and dividing it into 10 segments, this time it's the numbered gap just divided into 2 segments. So if you imagine going 50 mils divided by 2, my unnumbered segment is just 25. So far what I said is, where there are tick marks, I know each of these tick marks are off by give or take 25. If I came along and I gave you a reading, well, I'm reading that one here, I think it's 37.2, and I'm going to need to associate plus or minus, you might be able to think, oh yeah, it's about 37 or whatever, but you'll notice that this error here is humongous. We can still keep to the rule here. Usually, error is half the unnumbered division. Again, just a rule of thumb here, I'm going to let myself be wrong half up and half down, and it basically creates for me, if I'm at 37.2, I'm making this guess here, if I go half of 25 here is 12.5, by creating my own increment, if I go 12.5 up and 12.5 down, I've created the size of a tick mark, and I know at the very least I'm guessing 37, and I'm now centering a new set of tick marks. It's the size of 25, half wrong up, half wrong down, but I should at least know it within that precision. So that's why this usually half the unnumbered division is helpful. But you'll notice here, because the unnumbered divisions are still so wildly separated, it's not as nice as in the ruler case. Now we need to do our last manipulations here. We're going to round our errors, even though we did that process. Round errors to 1 sig fig. In chemistry, you can just round it to the nearest number. Because this is going to be a buffer anyways, yeah, the rule of thumb, plus or minus 12.5, not that bad to say plus or minus 10. I know in physics, they always round up, because again, if you round down, you better have a good reason to justify that. But that's plus 10. I then, therefore, even if my measurement, I thought I could get 37.2, because my uncertainty, because my error is in the tens position, I now need to round my precision also to the tens position. So while I wouldn't be surprised if you see in a textbook here something like 37 plus or minus 10, this doesn't actually match up to our sig fig stuff that we said earlier. This one, if I'm guessing at the ones position, would mean 38, 39, 36, whatnot. But if the error could be, no, it could actually be 40, 50, it could actually be 20 and whatnot, we're going to then round it here. Well, 7 is bigger than 5, so we're going to round it here, 40 plus or minus 10. So really low precision, not that it has to have 1 sig fig, but that the guess that we have has to be lined up with the plus or minus guess position. This measurement here could have been a lot bigger. It could have been 240. That's totally okay, because it's the guess position that's at the tens position that's lined up with the plus or minus at the tens position. So that's roughly what you do. Again, if you're more confident than that, you can roughly make this error smaller, but just as a rule of thumb here, we've done twice. The error is usually half the unnumbered division. Half is going to be a 5. We're basically creating the size of an unnumbered tick mark around my guess. Let's just flip over here. Those are analog instruments. Those are when you don't have a digital display. For a digital instrument or an electronic instrument here, usually a little bit easier. So for a digital display here, maybe I have a mass balance. There's a display that reads in grams for us here. Some balances here are 1 decimal place scales. Some of them are 2 decimal place scales. Careful not to, as you're playing around with it, don't just push down on this randomly. You're going to blow the scale. You're going to blow the calibration. Let's say I have a 1 decimal place scale. Make sure it's 0 to begin with. So you 0 it or you tear it. Right? So you make sure that it's calibrated properly. You put your mass on top of it. Let's say I have a mass. Just mass of the container. Let's say this scale here reads 10.2. What you might find is when you have that equipment on the balance, you might find a slight flickering of this number. So I might say 10.2. If that's steady, usually our error is 1 in the last digit. So earlier for analog instruments, we said error is half the unnumbered division. For a digital instrument here, we don't need a half, we don't need a 5, we're just going to use 1. If this number here is staying constant at 10.2, there's no flickering at all, I can just say 10.2 plus or minus 0.1, right? Because if it went much farther than 0.1, I would see it flicker to 10.3, 10.1. If I'm really not seeing that, that's an error that has 1 sig fig that is lined up with my measurement. Now, if it is flickering, if there is a draft in the room and something like that, 10.2, 10.3, 10.2, 10.1, and it is jumping around, no problem. You can come along and make this a big error. But just as a rule of thumb, if it isn't flickering, you can just put 1 in the last decimal place. We can do something called weighing by differences in this situation. Usually when you're weighing chemicals, you don't load the chemicals directly on the pan itself. You have your container that weighs 10 grams. There's 2 things you can do. You can press 0 at this point. You can sort of get the scale to forget that this particular container is actually on there. Every beaker, although it may be qualified at the same size, they all have their own unique masses. But if I don't do the zeroing and I just kind of keep adding to it, I add a little bit of powder, and let's say now the scale here reads 13.6. What I do is just by differences, so that's just a wording that we do. We can weigh by difference. And essentially, looking at the picture, it's just saying, well, now on my balance, if I didn't zero it after the container was on, Now I have the mass of the container and the mass of the chemical. I would just subtract off mass plus chemical minus the container, and that will give me just the powder that I'm actually using. So hopefully that gives you a hint at how do we assign a plus or minus, how many decimal places do I actually keep my readings. Just make sure to keep track of errors should always be 1 sig fig, and it should always be lined up with the guess position. Lastly, for today's lesson here, you're going to see on the resources section a quick overview of graphical techniques. A lot of this you already know. I just want to make sure we're all on the same page here. So we'll scribble our way through this here and rehash some of the vocabulary. So when we deal with a graph, graphs are basically a visual representation, and it helps us see the correlation. It helps us see the relationship between variables. There's two main types of graphs that we're going to deal with. In chapter 2, chapter 3, we're going to actually be plotting out discrete data. In this case here, in chapter 2, chapter 3, we're going to plot, let's say, the radius of the atom in picometers. Let's plot it against the element number. So what I can do here is I can look up element number 1, what's the size? Element number 2, what's the size? Element number 3, what's the size? I can actually just plot out the actual radius that I get. In this case here, because there is no element 1.5, element 2.5, it's not just randomly I chose these numbers, it actually is discrete. You can actually connect the dots. The connecting the dot here doesn't suddenly apply, I suddenly have those element 1.5, 2.5, whatnot, but it allows me to track change a little better. If I see it jump upwards, I suddenly have a bigger radius. More so in chemistry, we deal with continuous sets of data. Hopefully we'll be able to do this lab together here. We're going to plot a data mass against volume. Experiment is basically going to take down a bunch of volumes. If you have this much liquid, let's say 1 milliliter liquid, the mass happens to this amount. 2, it's going to be this amount. 3 milliliters, it's going to be this amount. Although you may have only taken readings, let's say in this example here, on the actual milliliters, because volume is a continuous quantity, we can sort of interpolate. We can sort of figure out if the pattern follows, I can sort of get a straight line, and I can actually get a extrapolated value. If I had tested at 1.5, I didn't, but if I can test 1.5 and if it follows the pattern, I can still try to figure out what the mass is. So in that case there, it's continuous. I'm going to hopefully get a bunch of dots to minimize my random errors. Some dots here might be really high, some dots might be really low. If you see a dot that's way off, you can call that point an outlier. It basically falls outside the range of data. You can sort of ignore it. Most of the graphs that we're going to see are going to be straight line fits, so make sure you use a ruler, and then we'll match it up with mx plus b. In that case there, we plot it. We actually plot as what's called a scatter plot. Basically plot all the xy coordinates separately and then add the trend line afterwards. Use your ruler, try to aim for yourself. You might find your best fit line is slightly different from the person next to you. That's totally okay. Make sure your graphs have labels. So I'm plotting so far mass and volume. Mass is going to be measured in grams, volume in milliliters. We always want a title of the graph here. So the title, in general, it has the format y versus x. Whatever's on your vertical axis, in this case here, it's going to be mass. In the other case here, it's going to be volume. As you're labeling your axes, you don't really need to squeeze it up into really high corner, really odd corner there, especially when we staple it. Sometimes it gets hard to read. You can even put it in the middle of the axes. Doesn't really matter. Just make sure that label, that title is there, as well as the units that we're doing. They're just going to talk about some more terminology here. Graphs can be either sketched or drawn. A sketched graph basically shows you the relationship, but it has nothing that's scaled. It just generally gives you a qualitative comparison. It generally says, do they follow each other? Are they proportional? Or are they inverses of each other? So a direct proportionality, this is sketched because I don't actually have the markings along here. But basically here, when x is small, I see my y is small. As x gets bigger, we see that the y gets bigger. That would be indicative of a proportional relationship. Or what we call an inverse relationship here, when x is a small number, right? I'm not that far on the x-axis, you notice that my y-axis is actually fairly high. A graph that does this here would be like a pressure volume for a gas here. When you're under high pressure conditions, the size of the balloon, the size of the volume is actually quite tiny. As you then gradually increase the pressure, you squeeze the balloon, gradually it decreases. We call it an inverse, even though it may actually be a reciprocal function. So inverse just means opposite. In this case here, as you increase the pressure, the volume decreases. Again, mostly we're going to try to fit it to straight lines. There's a few little techniques what we can do to force it to a straight line, but in this case here, we're just tracking the trends. Especially if the numbers are all in the same power of 10, you might want to plot, let's say this is radius again, 1, 2, 3, but when I say radius, I might say these radii are all times 10 to the negative 9 meters. And that way I don't need to go 1 times 10 to the negative 9, 2 times 10 to the negative 9. Everything is scaled to that factor there. Sometimes in the units here, it might even say radius, it might even say divided by this 10 to the 9 meters, whatever. It's just trying to say when you have a graph, it should actually be dimensionless. If this number had meters and I end up dividing by meters, I'm just plotting just the pure number. So that's what it means by dividing by units. We don't usually want to keep it as a sketch graph. We want to then draw a graph, which is actually scaled up. We would have actually taken down some quantitative readings, actually plot the points that we have there. Don't force yourself to have a straight line. So for example, pressure volume graph here would actually be curved. Then do a best fit curve. Do a curve that follows your data the best. Here's some really important terminology for us here. For a fair test, we always want to have one independent variable. The independent variable is the one that I'm purposely changing. In my mass volume analogy, I may be going and selecting what volumes I'm testing. That's called the independent variable. I want to compare it against one dependent variable. This is the one that might change. In this case here, my mass might be different depending on how much volume of solution is inside. We are purposely changing. This is the independent, where I'm purposely changing volume, and I'm watching for a possible relation for the mass. For a fair test, again, I want one of each. Everything else, the remainder, should be what's called controlled. They should be constants. In biology, we actually call the condition a control. In chemistry, we can refer to separate variables. I'm maybe testing volume against mass. I'm going to keep the light intensity constant. I'm going to keep the pressure constant. I'm going to keep the overall temperature constant. Those are all controlled variables that you want to make sure. If you see any changes based on the variables you're testing, it's because of the one you changed and not because of a whole bunch of other control variables. Lastly here, just some more terminology. Because we are looking at correlation, we're looking at relationship. They either increase together or they decrease together. If they increase together, they're called proportional. How is proportional different from linear? A proportional relationship would be something like y is mx. There is actually no y-intercept. So we're going to see in our chapter 1 how we're actually going to rescale the axis, let us actually go through the origin, as opposed to a linear graph, which might actually just go through. It is a straight line, some higher, some lower, but there is a y-intercept. Usually y-intercept is some indication that there's some systematic problem. All your values are skewed in one direction. There is a correlation coefficient that you can actually measure for. If it is a perfect positive relationship, when one goes up, the other goes up, the correlation is a +1. When it looks like the graph here is just ... it's totally possible that it has no relationship. That's also a relationship. In that case, there is no linear trend. A -1 would be something they drafted out here. That's a negative linear trend perfectly downwards. It could be any decimals between -1 and +1. A strong correlation is necessary, but it's not sufficient for causal. So you say correlation doesn't always mean causation. Basically, if I see a trend, if I increase volume, the mass increases. It doesn't necessarily mean volume actually causes the mass to increase. In this case here, it does, but all we can say so far is just a relationship. When one gets big, the other gets big. The actual causation, you may actually need to look at different things. If it does happen to be a straight line fit, we just do mx plus b. M, we know it to be the slope or the slant of the line. We sometimes call the slant the gradient. And this one here is change in y over change in x. It's rise over run. If you want your formulas, y2 minus y1, x2 minus x1. You could also, especially when you're doing this on computer, you can also plot out an r² value. It's similar to this correlation coefficient r. That's what they call this one here. They can give you an r² value. The closer your r² value here to a 1, it means a perfect match. Whereas if my r² here is like, 0.86 or something like that, it means the correlation isn't as strong. It isn't as quite, some of your dots here are leaning off the line, and those might be some outliers. The error propagation stuff we're going to get to in a later lab. In that case there, maybe I'll go over it with you in a second here. And then outlier, we talked about it's a point that doesn't follow your graph. A tangent is basically a line that follows your curve. If I have a curve and I'm interested to find the slope, slope inherently needs 2 points. For a tangent, however, I might want to find the slant, and basically I'm going to use a ruler, draw a line that basically follows your curve so that if I zoom in, my red line essentially follows the green line. So then I can pick any 2 points on my red line. I can figure out the slant for this one instantaneous point. We're going to use that a lot for rates of reaction. We deal with interpolation and extrapolation. Interpolation means I've taken down a bunch of data. Your graphs will look a little bit better than mine. I may have only taken readings at a few different x readings, but if I'm interpolating, if I want what's this reading in between, I might be able to say, provided the pattern follows what I just found, I can interpolate to find all the values that I haven't found. If my set of data here was only from here all the way to this x, if I extrapolate, if I pretend that pattern continues to follow after, this is then called extrapolation. Usually if you interpolate, it's a little bit more confident because I at least have some readings to sort of justify that the trend still follows. Extrapolating is typically a little harder. On the back side is just some rules for good graphing here. You can look through those sections, make sure you have titles, make sure you have units. Usually choose a scale that's easy to read in multiples of 1s, 2s, and 5s. Make sure you keep the same scale, although the scale on the x doesn't need to be the same as the y. Make sure everything is evenly spaced. Let me just come back to this last point here, seeing as I have it on the board. How do we do error for your slope? So the lab that we can hopefully get to here, when I'm plotting mass versus volume, it's possible when I have a few points that there's actually a plus or minus in mass. That's going to be the error in mass. There's going to be the plus or minus in the volume as well. Let's say for simplicity I just have 2 points and I'm interested in finding, well, what is the slant? In this case here, the chemical, if I took a change in mass divided by change in volume, hopefully you can be able to say that's going to be a density. It's true. Each of these points by themselves is already a volume, is already a mass. I could already do a mass divided by volume. But just in case some points are high, some points are low, I've taken down a bunch of readings, and now I have a best fit line that hopefully minimizes some of those random errors. This part's going to get a little bit hard here. We have the slope of the best fit. That's going to be your density, no problem. In terms of the plus or minus, what we're going to do is we're going to do that plus, associate half the range. The range is given by the max slope minus the min slope. Remember when we were doing this on averages here, we said, well, the range is how bad can it be on the extreme big or extreme small? Because the average is going to put me in the middle, going half wrong up, half wrong down should cover all of it for me. The only trouble here is all of these are actually slopes, so you need to do a y2 minus y1 rise over run calculation for all of these ones here. How do you get the max slope? I'm just going to finish off with this one here. A maximum slope is a slant that's steeper than what I've drawn here as the best fit. So far, my best fit is sort of this middle line. Hopefully, you can find 2 points that actually have the error bars that are intersected by this. The max slope, what you're going to do is you're going to take the lower limit of the first point, and you're going to try to go to the upper limit of the next point. Use a ruler for all this, or actually look at your data set to actually figure out what this would be. This would be sort of like your coordinate may have been x coordinate 1 plus or minus, let's do 1.0 plus or minus 0.5. My mass maybe 2.2 plus or minus 0.6. For this, because it's a vertical error bar, I'm going to look at the mass, so the y coordinate. To take the lower limit, I would go 2.2 minus 0.6. Oh, the lower limit here actually has the coordinate 1.6. So that's the lower limit there. On the other coordinate here, again, making up numbers, 5.0 plus or minus 0.4, 7.2 plus or minus 0.6. Again, it's a vertical error bar, it's a y error bar. I'm going to take the upper limit, that's going to be the upper side of that. When I calculate the slope, I'm going to use 7.8 as my y2 and my y1 as actually 1.6. That line there is going to be called your max. There's no change to the x, it's still exactly on the same coordinate. I'm going to calculate that slope, and I'm also going to construct one other line. If I only have vertical error bars, I can go from the top error bar of the first point to the lower error bar here. That would be a slant that's actually a little bit more narrow. If you do have x error bars, another common technique is to go to the left-hand side of the left point to go to the right-hand side of this point here. All we're trying to do is we're trying to come up with a line that is roughly more shallow than your best fit line. We're going to get the slope of that shallow line, and that's going to tell you how slanted, how shallow could the slant have been to calculate the lower limit on the error. So hopefully we'll be able to practice through the lab for that one there, and that would give you some sense of the error. You would take the x error, so 1, this is the x coordinate, take the lower limit, so 1 minus 0.5 says, oh, this side here would be at a 0.5, or the upper limit of the other point here, 5 plus 0.4, so that one there, upper limit would be 5.4. So lots of slopes for you to calculate, but that somehow helps us calculate the error propagating through these multiple points. So have another look over, and then if you have any questions, just let me know. Thanks, guys.